Welcome to Chapter 2 of Calc 1, still within our first week of the semester. This is going to kind of start building the foundation of calculus. The most basic thing that we're going to learn with calculus is what we're going to kind of see today, kind of in a practical way that we're going to talk about a couple things that we will see later on, but it gets us a good start and a good foundation. All of calculus is based on the idea of a limit, and hence that's what we're looking at here in section 2.1, the idea of a limit. Limits are the first concepts taught in calculus, but are the underlying definition of the two fundamental operations in calculus, which is differentiation, which we then calculate derivatives for that, and integration, where we are evaluating integrals. It is essential to develop a solid foundation on limits, and the idea behind this will flow all the way through this course. The first section illustrates how limits arise in two unrelated problems, first by finding the instantaneous velocity of a moving object, and then by finding the slope of a line tangent to a curve. Those are some big ideas that we will kind of really hone in on later. Average velocity and instantaneous velocity. So I'm going to kind of do them together because they end up having kind of the same idea together when we talk about average velocity and instantaneous velocity. Now, suppose you wanted to calculate your average velocity as you travel along a straight highway. If you pass milestone 100 at noon and milepost 100 at noon and milepost 130 at 12:30 p.m., you have traveled 30 miles in a half hour. So your average velocity over this time interval can be found by taking the 130 mile post minus the 100 mile post to calculate how many miles you drove, and take the 12:30 p.m. minus the noon, which tells us that we have half of an hour. Okay, so this is miles and this is hour, hence the miles per hour to create a velocity. And so what I get is 30 over 0.5. We divide that out, and we see that our average velocity is 60 miles per hour for that interval from noon to 12:30, okay? On the other hand, it is certain that your instantaneous velocity, which means the speed indicated on your speedometer, varies from one moment to the next. So when we talk about average velocity, we're talking about over an interval of time. When we talk about instantaneous velocity, that's when we're looking at our speedometer at 1 single second. What is your speed at that time? Okay, so that's kind of the main difference of those two. Average velocity, we don't need calculus for. Instantaneous velocity, we need calculus for. Okay, so for the average velocity, to compute an average velocity, use the position of the object at two distinct points in time. Given any time interval, here we're going to use some interval notation from t0 to t sub 1, those are my two times, then the average velocity is found by, what do we do up here? We took a difference of the miles over the difference in the time. So the average velocity, you want to do it that way, is equal to s of t sub 1 minus s of t0 all over t sub 1 minus t0. Okay? Where s of t is the position function, or the position of that object at any time t. So just like when I talked about the position of the milepost, that is what the s of t is. Okay? So we have this example here. We have a rock that is launched vertically upward from the ground with a speed of 96 feet per second. Now, neglecting air resistance, the position of the rock at t seconds is defined by this position function. So, the position s is measured in feet, with s equaling 0 corresponding to the ground. So, the position at 0 is that you're on the ground. Find the average velocity of the rock between each pair of times. So this is an interval from 1 to 3 that I'm looking at, and this is the interval from 1 to 2. What is the average velocity? So by our definition, we have to subtract the function value at each of those times over the subtraction of the time. So here, I'm going to do my average velocity is equal to S of 3 minus S of 1 all over 3 minus 1. Bam, that's the formula. The hard part now is to take that and plug it into the function and figure out what those values are and not make a mistake along the way. So if I put 3 into there, okay, wherever I see a t, I'm going to put a 3. We get negative 16, 3 squared plus 96 times 3. That is just S of 3. Minus negative 16 times 1 squared plus 96 times 1. That is S of 1. All over 3 minus 1, which is giving me a 2. Okay, now this again is the hard part, that you don't make a mistake. If you take your scientific calculator, if you have a graphing calculator, you're more than welcome to throw that in. Use your parentheses if you would like, and we get 144 for that first one. Minus, do the same here. Whenever you do that all the way, this gives me negative 16 plus 96, so that piece is just an 80. Minus between them all over 2. When I subtract, I get a 64 all over 2, which is 32. We are in feet per second here as our unit. So that is my average velocity from 1 to 3 seconds. Okay, over time, what is the average velocity? If I try to do that here for my second interval from 1 to 2, then my velocity is found by doing S of 2 minus S of 1 all over 2 minus 1. Well, that's nice in the bottom because that gets me a nice 1. Now, we already know what S of 1 is. S of 1 is 180. So basically, I need to do negative 16 times 2 squared plus 96 times 2. I'm going to steal the 80 from the other side, from the other problem. And when I do negative 16 times 4, that gives me negative 64. Add that to 182. That will end up giving you a value of a 128 minus the 80 all over 1. Therefore, we get 48 feet per second. So that is the average velocity from 1 to 2 seconds. Now, does that make sense? The average velocity faster as you start going from 1 to 2 seconds versus 1 to 3? Yes, if you go 1 to 2 seconds, kind of get some speed going, then you kind of flatten it out afterwards, okay? All right, now, an important observation here is that the average velocity is simply just the slope of the line that joins the points on the graph of the position function. So we're talking about here a projectile, and if you were to actually graph that, you would end up having something that goes up and comes back down. And so from 1 to 2, or from 1 to 3 seconds, I'm not exactly sure on this one. I'd have to find exactly where they're at. I could have that as my 2 points, and so what I'm looking at is just the slope between those 2 points. Okay. Now, the instantaneous velocity, let's expand upon this. The instantaneous velocity at a point t equaling t naught is determined by computing average velocities over intervals from t naught to t1 that decrease in length. Okay, let me say that again. This interval, we're looking around this t naught, but I'm decreasing this interval. So if this is from 1 to 3, the next decrease would be like 1 to 2, and then 1 to 1.5, 1 to 1.1, 1 to 1.01. You're decreasing that interval each time. So as t sub 1 approaches that t naught, then the average velocities typically approach a unique number. This is what we refer to that as the instantaneous velocity. Now, this single number is called a limit. Oops. I can't see with it being delayed. Oops. Okay, we're going to do that. How about that? Okay, so, like I said, once those values keep getting smaller, 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 whenever we do that, they're getting closer and closer and closer to one value, and we'll see that here in just a second. Now, the easiest way to see the limit is to do a chart of multiple values that are very, very, very close to the x value that's in question, okay? So again, average velocities is the slope between 2 points. y minus y over x minus x. Instantaneous velocity, we have to decrease that interval length in a way that we approach a unique number. Okay, so we're going to do this by a chart. And you're going to want your scientific calculator to help you out quite a bit here. Okay, so we want to estimate the instantaneous velocity of the rock in the previous example at a single point t equaling 1 using the following numbers. So here's my intervals, and what are we doing? We're decreasing the length of these intervals. This is a length of 1, this is a length of 0.5, length of 0.1, 0.01, etc., etc. Okay, so what we should find along here with my average velocity is that we're honing in on a single number. Okay, so let's do that. To find the average velocity, we do s of 2 minus s of 1 all over 2 minus 1. If you recall, we just did that. It is 48 feet per second. If I try this interval, s of 1.5 minus s of 1 all over 1.5 minus 1. So remember, this is 80. This here, you're going to have to plug into that function, negative 16t squared plus 96t. I know it's kind of tedious when you're working with these decimals, but it gets the idea across really, really well. So if you do that and divide by 0.5, I will tell you that the average velocity for this interval is 56. Likewise, we're going to do this 4 more times. S of 1.1 minus S of 1 all over 1.1 minus 1. So we're going to find out what this is. Subtract 80 from it, divide by 0.1. I will tell you that that average velocity is 62.4. Continuing on, same idea, y minus y over x minus x. Multiplying that within that function, adding it all together, subtracting from the 80 of S of 1, you get a 63.84 when you divide by that 0.01. You get the idea, hopefully. I mean, if you want to write it all out, that's fine. I will write it all out just so that you have it. If you do this, you will get 63.984. And the last one, S of 1.0001 minus S of 1 all over 1.0001 minus 1. Then you get 63.994. So look at our average velocities. We start with 48, we go down 56, or we go up, 62, 63, 63.98, 63.9984. If we were to try something even closer to 1, this number is going to be honing in on what number. Basically, you can kind of round it to what it's going to. Therefore, a reasonable estimate for the instantaneous velocity, that one single velocity at t equaling 1, is 64 feet per second. You're never going to get the actual one. You're just going to get what it is approximate to, okay? So the idea of a limit, we're limiting towards that 64 feet per second. So when we do notation, the instantaneous velocity, as if we'll do that, is going to be found by taking the limit as t goes to 1. So we saw this notation, or excuse me, this is kind of the notation for a limit. We haven't seen this yet, of the average velocity. So I'm going closer and closer to that 1 of the s of t1 minus s of t naught all over t1 minus t naught. That is found by doing the limit as t goes to 1 of what I just said, s of t minus at t equaling 1, so minus s of 1, all over t minus 1. And so this somewhat looks like one of those difference quotients that we found in one of our sections in chapter 1. And so this limit of my average velocity is coming up here to that 64 feet per second. Okay? So, average velocity, no calculus. Instantaneous velocity, we need calculus. Alright, so that's one of the bigger pictures. The other bigger picture we're going to talk in this section is on secant lines and tangent lines. So there's going to be a very similar secant lines. We don't need to know the slope, or don't need to know calculus to get the slope of a tangent line. The slope of a secant line. But we do need calculus to get the slope of a tangent line. Okay? So in chapter 1, we talked about two different types of difference quotients that we will be working with. In order to prove these expressions, one must use the slope formula for lines. And here for a secant line, recall that any line joining 2 points on a curve is called a secant line. The slope of a secant line is denoted by m, and we're just putting SEC for secant, so m is usually the slope. For the position function of the previous example on the interval of t0 to t1 is defined to be exactly what we were just working with the average velocity, except for in the context of a secant line. Now the secant line is found by doing s of t1 minus s of t0 all over t sub 1 minus t sub 0. Okay? And so here, this gives me the slope of my secant line, finding a y minus y over x minus x. So the first example that we were just looking at demonstrates that the average velocity is the slope of the secant line, and we looked at that before, on the graph of the position function. And so therefore, the average velocity is the same as the slope of the secant line. So let's see that position function. So I'm going to let this be my coordinate, this be my t-axis, this is my position function, and I end up having what we had back then was a projectile, so it does something like this. Generically, let's choose this point right here. Let's choose this point right here. I'm going to call this t0, my starting point. I'm going to call this my other point, or my other time for my point. Call it t sub 1. Likewise, if this is my time over here, this is s of t0, like I'm plugging it into my function, kicking out that number. Likewise here, plugging that into my function, so this distance over here on the y-axis is s of t sub 1. So if I create the line that is connecting those 2 points, then I have something that looks like that. And if I'm looking for the slope of that secant, that is the rise over the run. So here's my secant line. This distance has to be the difference in the y. So I need to take this one minus this one. So s of t1 minus s of t0 is this distance right here in this vertical sense. Okay? If I now also finding the slope, the rise over the run, I need to know what this distance is. Well, to find a distance, we're going to subtract t sub 1 minus t0. Therefore, the slope is found, let's remind ourselves, as the rise over the run. And that is going to be found by taking the rise, which is s of t sub 1 minus s of t sub 0, all over the run part on my graph, which is going to be this part right here. That is going to be t sub 1 minus t0. So making sure, again, for a secant line, we do not need calculus. We can just find the difference in the y's over the difference in the x. Okay? So, concluding, likewise when I did instantaneous velocity with average velocity, we're going to make these conclusions about our secant line and our tangent line. Each average velocity in the table on the previous page corresponds to a slope of a secant line. So if you saw this that we did here, we did 1, we did 1.1, 1.5, and so here are all those slopes that we saw within those lines, okay? Just as the average velocities approach a limit as t approaches 1, the slopes of the secant lines approach the same limit as t approaches 1. And here's the biggies. As t approaches 1, the secant lines approach a unique line called the tangent line. The tangent line intersects only at one spot. One point, one spot. Okay, or one point. And the slope of the secant lines m subsecant. Approach the slope of the tangent line, we're going to represent that by m subtan, at the point 1, s of 1. Therefore, the slope of the tangent line is also expressed as a limit. Okay, so notice here we have all these green lines connecting secant lines. And then I get to this red line, which gives me the slope of a tangent line. And that right there is only going to intersect at this point right here. They're not going to do a secant line here. It's not going to be a secant line here or here. It is just going to be intersecting at one spot. Again, calculus with the tangent line, no calculus with the secant line. All right, now this limit is the same limit that defines the instantaneous velocity. So where we saw that the average velocity equals the slope of the secant, therefore the instantaneous velocity at t equaling 1, that's for this example, is the slope of the tangent line to the position of the curve at t equals 1. So that is huge. You got to remember that as I find the slope of the secant lines, I can do y minus y over x minus x, but until I reach that limit, that is the point at which that line is tangent to that curve. So as t approaches 1, the slopes of the secant lines approach the slope of a tangent line as t goes to 1, the average velocities approach an instantaneous. I can spell that without seeing it. Instantaneous velocity. Okay? All right. Very good. Okay, so if you go into my lab math, you should be able to see some figures here. On page 42, there's a figure 2.6 that I'm going to pull up and show you to kind of get a good idea. This gives a really, really good picture of that. So, if, scrolling here, here we have the average velocity s of t1 minus s of t naught all over t minus 1. There's a secant line. What happens? When I move that closer, what happens is that average velocity those secant lines end up getting straight down to this tangent line. So this is a nice visual for you to be able to see that. Okay, so let me pull up another program for you to see as well that will show you this idea kind of moving. So this is kind of cool. Has me a little slider here that I could use. Notice here, here's the slope of that secant line, here's the slope of the tangent line, and see what happens whenever I get further away from x equaling 1, I get a slope of 40, but as I get closer and closer and closer to 1, then I get very, very close to that red line until I can get right on it at x equaling 1. We're off just by slightly. Won't let me get on exactly x equaling 1. And so there you can kind of see that difference there. As well as, let's see, right here, here's kind of that line as well. Again, you can kind of see how it goes over. It gets bigger, bigger, bigger. And then, as we get closer and closer, we limit to that tangent line where slope is equal to 64. Okay? All right, so that's some good stuff there. Let's finish this set of notes by looking at these two functions and making a conjecture about what our instantaneous velocity is and what the slope of the tangent lines are for each of these. So I have a position function here, and we're going to get close to t equaling 2. Here I have a trig function. We're going to get close to x equaling 0 over there, and we'll talk about the slope of a secant line into a tangent line. So for the average velocities, remember, we're going to kind of compute those without calculus and then see where the average velocity is getting closer and closer to in order to identify that instantaneous velocity. So if I'm wanting to hone in around t equaling 2, I may start with an interval of 2 to 3. Then I may cut that in half and go from 2 to 2.5. Then let's get down to the idea where we get down to a tenth of a way, so like 2.1. Then we can go to like 2.01 and 2 to 2.001. So we're really just honing in onto around one side. No matter which side that you choose, you would be able to get the same value as well. So that means I need to find my instantaneous velocity. Let's go s of t minus s of 2 all over t minus 2. So this is what we're wanting to find. So I'm going to take 3 and I'm going to plug it into here. And you're going to find that that's going to be 96 minus s of 2. If you put s of 2 in there, you also get 96 all over 3 minus 2, which is 1. Therefore, that average velocity is 0. This means we have a horizontal line there for the secants. If I look at 2.5 and plug it in here, that will give you 100 minus 96 all over 0.5. And if you compute that, you get an average velocity of 8. If I put 2.1 in and subtract from s of 2, I get 97.4 minus 96 all over 0.1, which equates to 14.4. If I then plug in 2.01, I get 96.1584 minus, minus 96 all over 0.01, which equates to 15.84. And if I look at the one that's as close to 2 as I am identifying here, I get 96.015984 minus 96 all over 0.001. And if you do that in your calculator, you are going to get a value of 15.984. So what's happening? I go from 0 to 8 to 14.4, and I'm honing in on what kind of whole number, and our instantaneous velocity for this one is going to be 16. I don't have a unit there, so there's not one expected to be put there. Okay? All right. Do the same type of exercise except for the idea, the concept, we're looking at slopes of secants, and then when we limit down into around x equaling 0, we will then get the slope of the tangent line. So I'm going to, coming in again from the right, hone in on 0. So I'm going to just look at the positive side to the right of 0. I'm going to go 0 to 0.1, or to 1, excuse me, then 0 to 0.5, then 0 to 0.1, then 0 to 0.001. Oops, I'm off. 0.01 is what that should be. Trying to add too many zeros in first. And then 0 to 0.001 would be my final interval that I have there. Now, the function this time that we're looking at is a sine curve. It has an amplitude of 3. So if I were just to sketch that graph, we would go up, back down, and up. This would be at 3. The bottom would be at -3. That would be kind of a graph, a sketch of that. So again, we're going to take these values, put 1 in for x. We're in radian mode, so if you're finding your values here, make sure your calculator's in radian mode. We're going to do 3 sine of 1 minus 3 sine of 0 all over 1 minus 0. And if I do that, then I will end up with 2.5244. If I plug in 0 and 0.5, do the 0.5 first, I get 3 sine of 1/2 minus 3 sine of 0 all over 0.5 minus 0, which is still going to be 0.5. Then I end up with a slope of the secant line of those two x values as 2.87655. And you keep doing that. I'm not going to waste the time to write the 3 sine of 0.1 minus 3 sine of 0 over 0.1 minus 0. I'm just going to give you those values. This becomes 2.995. This slope of its secant becomes 2.99995, so 4 9s and a 5. And then when I computed this one here at 0.001, it's one closest to there, I get 2.999999, and then I just put a dot, dot, dot. So notice here that I'm looking at values of 2.52 all the way down to this 2.99999. If I want to limit, what value am I limiting to? Hopefully you're telling me that that's awfully close to 3. Therefore, we're going to state that the slope of the tangent line for this graph is at 3. Okay? So this is the idea, first idea of that limit, and that will conclude our first week. We are going to then move into kind of the definition and start looking at limits graphically, as well as some more tables, as well as analytically being able to figure those out. So exciting times coming forth. I will see you next time.